Good morning. Today I'm going to be competing in round 652. I'll be mostly competing during the contest, and then after the contest I'll go over solutions. So if you're interested in those, you can skip to the end. But good luck, have fun. Lee's going to fashionably decorate his house for a party using some regular convex polygons. My favorite. It's beautiful if and only if he can rotate it in such a way that at least one edge is parallel to this axis and at least one edge is parallel to this axis at the same time. Can you do it? So you need to be able to divide it into fourths, I think. If n mod 4 is 0, then you're good. Yeah, I think that's it. It's pretty clear why that's true, but I'll explain at the end. Alright, the string he found was a binary strength of length n. In one move, he can choose, there we go, choose 2 consecutive characters, and if this is 1 and this is a 0, he can erase exactly one of them. He can choose which one to erase, but he can't erase both simultaneously. Okay, so if you've got a 1 and a 0, you can replace it with something else. So now what's the question? He thinks 2 different strings, x and y, the shorter one is cleaner, and if they're the same length, the lexicographically smaller one is cleaner. Print the smallest you can get. Is that it? So this can't do anything. This one, you can erase the 1? Yeah, okay. So if we use like a stack, well, we're going to have a series of 0s and then a series of 1s, right? And then we can remove a 1. Oh, I guess it's just all of the 0s and then all of the 1s from the back to the first 0. So 1 or 0, 1, yeah. Okay. Is it multi-test cases? So int length or int n equals this. Line equals this, int prefix equals 0, int suffix equals 0. So if it's all 0s or all 1s, then we just print the whole thing. So now, if not has 0s or not has 1s, then print out the line. Otherwise, it's got both 0s and 1s. So int earth4.0 is less than n plus if line I is equal to 1. Then e prefix equals I, break. And we're going to do the same thing pretty much backwards. So start at the last character, go to the beginning, and if it's equal to 0, then set the suffix equal to I. So now we get the number of prefixes in the beginning, suffixes in the end. Yeah, okay, so now if z pre plus plus n minus the suffix, that'll give us the prefix length. I guess this has a +1 in it. +1, okay. So if this is greater than n, then it's just all zeros and all ones. Then sysout line, continue. And then otherwise we're fine. So otherwise for 0 as less than z pre plus, or yeah. Then sysout line at I. And then after the prefix, for int I equals suffix I is less than n, I plus, so line at I. And let's see if that's right. Yeah, that looks fine. Guess there's one more case I want to check. So that should be fine. All right, we have an array of integers and k friends. We'd like to distribute all integers in your backpack between your friends such that the ith friend will get exactly this many integers. And each integer gets distributed to each friend. And do they have to be like consecutive groups or no? Probably not. I don't think so. The happiness is the sum of the maximum and the minimum he'll get. I see. I see. So it seems like we want the maximums to be like scattered, but the minimums to be condensed. Seems like a greedy is plausible. So this person gets 1, this person gets 3. So we would want to do like 17 and then, yeah, 17 plus 17 and then 13 plus 1. What is that? 48. Yeah, so I think greedy is fine here. So 11 for each of them, and then 2 10s for each of them. That's 21 times 2, yeah. These are boring cases, okay. I think that should be fine though. I think the greedy works. Okay, n equals this, and k equals this, and then read in our array. Okay. And then we need to read in sizes. We need to sort these. And then 1 equals 0. So then for, okay, so yeah, so the last k things we need to keep. All the sizes are positive, right? Yeah. For into I in sizes, or yeah, sizes at I minus minus. Okay, so now we need to add the last thing of each group in. Okay, so then we need to greedily put things in the biggest group as possible. So for int group equals k-1, group up to 0. So then we want to put as many things as possible in here. So int next equals 0. Next plus equals sizes at g. And oh, I see. Yeah. Okay. So if sizes at g is not equal to 0, we need to do this. If sizes at I is equal to 0, then well, we need to do this the second time then. It'll be both the max and the min. Here it's not both the max and the min, which means we need to add it back in. Okay, so I think this should be fine. No, it's not. So this should be 17, 17. Oh, the first one. Yeah, okay. What? Size is it next? If next is less than n, do this. Why is this an issue? This should be a next. 48, 42, big number, okay. So this should be fine. Wait. Oh, darn it. Hopefully I don't get penalized for that. Yeah, okay. I think that should be fine. I think if you fail test 1. Pretty sure you don't get penalized if you fail samples, so that shouldn't be an issue. Lee's got a rooted dead bush of level n as a rooted, wait, what? Oh, we define this as a rooted tree constructed as defined below. Level 1 is a vertex. Otherwise, we make one of level I plus 1. Then for each vertex, if it has no children, add a child to it. If it has one child, we add 2 children. If it has 2 or more children, skip it. So 1, 2, 3. Oh, so it always has 1 child or 3 children. And that's it. Let's define a claw of a rooted tree with 4 vertices. Looks like a claw. Yeah, I can see it. So So he's got a rooted dead bush of length n. Initially, all vertices are green. In one move, he can choose a claw. And if all of his vertices are green, all the vertices of the claw are children of its center. And all vertices of the claw are children of its center. What does that mean? I think it just means it's a claw. Then he can color the claw's vertices yellow. So he colors these 3 yellow. He'd like to know the maximum number of yellow vertices he can achieve. Okay, let's see. The level. Oh, so this is like a massive tree. Print the answer under mod because it can be huge. I see. Okay. So if it's level 1 or level 2, it's 0. I see. Okay, what about level 3? If it's level 3, the answer is 4. You can get 4 vertices. So each time, I suppose, you get 4. So the answer is always going to be a multiple of 4.
Good morning, sir.
So multiple 4, well, it will be, let's draw out what this 4th one looks like. So it's the 3rd one, but then I guess they draw it here, or almost, that's almost it. Since we can't choose either single claw 1, 3, 2, 4 or this. Oh, we can choose either of these, but there are no others. So anything with degree 3 whose parent doesn't have degree 3 is what you want. So basically we just have to figure out how this grows, right? That's it. So 1 and 2 we can skip. Level 3 you get this. Level 4 you move down 1. What's level 5 then? So all that matters is the number of things with 1 child, or I guess that's not true. this is 3, this is 4, and this is 5. So dp at 5 equals like 2 plus dp at 3, because we get these two branches. And those are entirely disjoint from everything else. Then we also get this here. Well, I guess dp at 4 might be easier to work with. So like dp at 4 is equal to 2 times dp at 2 plus dp at 3. So now dp at 5 equals dp at 4 plus 2 times dp at 3. So do these wind up just being like Fibonacci numbers, kind of? Yeah, so if this is like layer x, then these are both x minus 2, and this is x minus 1. Yeah, so this is just matrix expo, I think. Oh wait, not even that. We can just process all possible answers easily. Okay. So let's pre-comp everything. Int max equals so what we can do is, well, ansat 3 equals 1, and then 4 int I equals 4, I is less than max, plus ansat I equals 2 times ansat I minus 1 plus, or I minus 2 plus ansat I minus 1. Under mod. Oh, this also won't be right. Yeah, this isn't right. Although we can just multiply it by 4. But I don't think that's right. Yeah, so this part's not right, and the reason it's not right, this also is not right. The reason why is because we're not counting some things that matter. Like, we're only counting the leaf clause, but we can count more than that. Yeah, so Boolean array using top long x. Boolean array. So using 3 equals true. So 3 we use it. Okay, so now if using top at I minus 2 or using top at I minus 1, then using top at I equals false. Otherwise, if they're both false, then using top at I equals true, and set I equals set I plus 1 under mod. And then we should be fine. Eight 7, 8 4. Okay, yeah, that's fine. I think an accurate description of that problem might be tedious. You could also definitely do it with like 10 to the 18th bounds. Like bounds were way too small in my opinion for that. But oh well. Alright, he bought some food for dinner time, but Lee's friends eat dinner in a deadly way. Or maybe you can't. Maybe and statements are difficult. No, that's super predictable. Okay. You could, I don't know. I feel like bounds should have been bigger for that problem. Oh well. There are n different types of food, and Lee has m best friends. Lee has wi plates of the ith food, and each friend has 2 different favorite types of food that are different. Whoever's called into the kitchen will try and eat 1 plate of his favorite food types. Does he choose? Which one does he try and eat? If a friend will eat at least 1 plate of food in total, then he will be harmless. But if there's nothing left for him to eat, he will eat Lee instead. Lee can choose the order of the friends to call. Which one do they eat? Oh, 1 plate of each. I see. If a friend will eat at least 1 plate, then he's fine. But if he eats both, he's in trouble. So you want like as many people as possible to eat only 1. That's the idea. Yeah, okay, so you take the 1 and 3, then you take 1, 2, and 2, 3. I see. That's not super obvious how to do this. Like, you wanna, if yes, the order is interesting, I guess. Maybe it's a graph problem. Multi-edges. So there are multiple ways of doing this, though. You can do this one first, then this, then this. Let's see. Well, yeah. Okay, this does have solves. Maybe let's read the last problem just in case. 1 versus 1 game with T rounds. Each round has 2 integers. The integer SI is written on the board at the beginning of the corresponding round. Each turn a player will erase the number on the board. Let's say it was A, and we'll write either 2A or A plus 1. Either multiply by 2 or add 1. Whoever writes a number strictly greater than E loses, and the other one wins the round. Is this a game called Critic? Oh, okay, yeah. You want to play against Ice Bear. For each round you choose 2 things. Lee will start the loser of... Whoa, the loser of each round will start the next round. Huh, so you might want to be the loser. The winner of the last round is the winner of the game. The loser of the last round is the loser of the game. Well, yeah, so I suppose this is exactly how to do it. I think this makes the problem even easier, in my opinion, telling us this. So for each round, we need to know whether you can win it and whether you can lose it. This problem seems a lot easier to me than E. It seems like what you should try, like the approach you need to take is pretty obvious. So you need to like just do it. Okay, so let's say, well, let's say you've got like 10. And then you want to figure out for each number all the way down to S, what is the state? Oh, maybe this is our Matrix Expo one then. We should be able to figure this out in log time. Should be pretty predictable in log time. So, what about 9? Let's look at 9. So 9 can lose, and it can also win. So 10, like, let's make 2 categories, whether it can win and whether it can lose. So 10 can neither lose or 10, I guess 10 can lose, but it can't win. 9 can lose, but it also can win. 8 can reach 9 or losing, so it can lose, but it can't win. Yeah, and this should just alternate by parity. 7 can reach 8, which can't win, so 7 can win. 7 can also lose, so then 6, 5, I guess 5 is where it gets interesting. So 6 can't win, but it can lose. 5. 5 can hit 6. So 5 can win. Can also hit 10. Can 5 lose? Well, 6 is gonna win. 10 is also gonna win. So the answer for 5 would be no, it can't lose. Like if you're trying to lose, then 5 either hits 6 yeah, if you're trying to lose, that means if you get to 5 you lose, because if you get to 5 then you get to 10. Like if it's your turn on 5, you hit something 6 through 10 and then the other person doubles. I see, okay. So then 4, then I guess this just repeats like 6 through 10 for a while. So 4 can lose because 4 can go to 5, which can't lose. 3 can go to 6, which can lose, or it can go to 4, so 3 can't. What about 2? 2 can go to 4, which can lose, or 3, which can't, so 2 can lose. And what about 1? 1 can go to 2, which can lose, or 2, which can lose, so 1 can't lose. So we should be able to answer this problem right here. Oh, or I guess this is just one round. Yeah. All right, what about 4? So, can 4 win? So 4 can reach 5, which can win. It can also reach 8, which can't win. So that's a 1. 3 can reach 6, which can't win. So that's also a 1. 2 can only reach winners, so this is a 0. Yeah, I see. So it's going to be like 1 0 1 0 1 0, then a bunch of 1s, then a bunch of 0s, I think, or then 1 0 1 0 1 0. Yeah, so it's either going to be, let's see. It's either going to be alternating or it's going to be all 1s. Alternating starting with 0 even. Oh, and correspondingly the other thing is the opposite. Okay. When might that break? Maybe for 8. So if we're at, well, let's try 8. Yeah, 8, 7, 6, 5, 4. So can 8 win? No, can't win, can lose. 7 can win, can also lose. 6 can lose, 5 can lose, 4 probably can't lose. Yeah, okay. What about 6? 6 can not win, 5 can win. 4 can hit 5, which can win. Can also hit 8. So this is a 1. Yeah, alright, so I think that's it. Yeah, so I think this is the way to go for me, at least, because I see how to do it. I don't see how to do E, but that's fine. All right, so one test case. Rounds equal this. Oh wait, this shouldn't be this. 2. Yeah, okay. So static into play. I guess this will be a boolean, right? So returns whether small is a 1. Okay. So yeah, so initially we did this. Okay. So int switch, int change, I guess, gonna be equal to big over 2. That's 5. It'll be 2. What if it was something like 9? So 9 is 0, 8, 7, 6, 4, 3, 2, 1. So 9 is 0, 8 is 1, 7, 0, 6, 1, 5, 0, 4, 4 can reach 8, or it can reach 5, so it's a 1. 3 can reach 6, or 4. Yeah, okay. Alright, so int smaller equals big over 2. Oh, I guess if it's odd, that's always going to be the case. So if big mod 2 equals 0, and we start with 1s, and we don't start with 1s, we start with a 0. That means it just alternates forever. So in this case, we return small, or big minus small, mod 2 is not equal to 0. Okay. So now if it's 9, it starts with a 1. Or maybe it's 10, starts with a 1. well, okay, 5 starts with a 1 is a good example. So int next relevant is going to be equal to the big number divided by 2. So then if, well, yeah, okay. So if small is greater than next relevant, so then I guess there's one more case. Okay, so if small is, or yeah, if it's greater than the next relevant, 5 divided by 2 is 2, yeah. So if small is bigger than the next relevant, then return true. Otherwise, return play of next relevant, small, false. Or, yeah, false, okay. So now we have one last case. So this is otherwise, else, if not start ones, and big mod 2 equal to 1. Wait, this was equal to 1. This should be equal to 1. So now if we start with something like 10, then yeah, so int half will be equal to big divided by 2. So then if small is bigger than half, it's bigger than or equal to would be fine. Then return small, or return big minus small. Mod 2 does it need to be equal to 0 or not equal to 0? Not equal to 0. Otherwise, then we can just return play from big, or from, sorry, from half to small with start ones. Because these are the only two cases. If it's equal to, or this should be equal to 0. Yeah. Okay. So, awesome. So now, calculate whether we can win. Yeah. Static boolean play all. Very big, very small. Well, I guess this is kind of just implicit here. Okay, so you go first, right? The answer can be 0, 0. Well, all right, what if the answer is 1, 0? yeah, I guess now is the actual thinking part. Okay, so we'll keep this because this is helpful. Yeah, how does this work? If you win, then you start the next round? The loser starts. I see. Yeah, okay. So for int r equals rounds minus 1, r squared equals 0, r minus. So we want to know, okay. So if you start, well, Boolean can win. If you start this last round, then you can't win. Boolean can lose equals true. If you start this round, you can lose. Or I guess, what is it? Is it can win and can lose? Yeah, I guess it's whether you can force it, right? Okay, so now so this is going to be Boolean, it's going to be win side equals play and big at r, small at r, and start with zeros. Yeah. What's wrong with this? Oh, false. Okay, and this is going to be the lose side. It's going to be this, but we start with ones. Okay. So now the person who starts can win. Person who Boolean next win equals something. Boolean next lose equals something. Okay. So, or do we want to go from the beginning? Man. Ugh, this is not hard. I just can't think through it. This is like just like easy logic. Okay. So we have the results from the future game. Like we have whether we can win and whether we can lose at this state. So we can win if either we can lose. I guess this is win now, right? This is lose now. So how do we win? Well, we can win if we can win, and we can lose now. That's one way of winning. The other way is if we can win now and we can't win in the next turn. Yeah. All right, how do we lose? We can lose if we can lose in the next turn, and we can lose now. So if we lose now, then we go first. We can lose again. Or we can lose if we can win now, and the opponent can't lose on the next turn. This is going to take a while to debug, but I think that's the general idea. First one should be 1 if you can win, second one if you can lose. Okay. And this is just so insanely complicated. 0, 0. This would be super great if this were right. Oh no, really? 1, 1 should be 1, 0. Okay. So remember that whoever writes an integer greater than e loses. Yeah, so this is wrong. Okay. All right. 8. So 8 is can win, can lose. Can 8 win? No, can't win. It's gonna have to lose. 7, 6, 5. 7 can win. 7 can also lose. 6 can win. No, 6 cannot win. But can 6 lose? Yeah, 6 can lose. 5 can not win. Wait, 5 can win, yeah. And 5 can also lose. What about 4? 4 can win. Can 4 lose? No. So I think I found the problem right here. I think this is the problem. If you don't start with 1s and big mod 2 is equal to 0, yeah, then this should be if it's greater than half. 1, 0. Awesome. Let's check all of these again. 1, 1, 0, 0, 0, 1, 0, 0, 1, 0, and moment of truth, this should be 1, 0. Reading longs, thank you for the test data. One, 0. Second place, dude. Let's go. Nice. All right, let's pull our Raid Wish and solve set. Did Raid Wish solve the game theory first? Yeah. Okay. All right. So this is what's left. We can do it, I think. Yeah, we're done with this. Okay. So well, let's get clean paper. All right. So how do we go about doing this? We want to online IOI 2020, right? Can we go backwards maybe? Yeah, maybe going backwards is easier. Because when you go backwards, you add to one of the edges, right? You're adding to one of the edges, and you just want to make sure the total never gets too big. Oh, I guess that's just an equivalent problem. Well, what does it look like if you solve it backwards? So if you have two positions, well, sorry, how are my friends doing? They're doing all right. Good to see. Good to see. All right. So if you go backwards, then the last thing you take might be a 1. I guess it's tricky because like the last edge you take, it could be just one thing. It could also be both of them. Are there any other constraints here? Do we just want to pick some ordering of the meals, maybe? That might be the case. If we have some meal, like if we've got some node here, and I'm gonna go to the bathroom. Be right back. Yeah, so if we have like if something is already empty, then we have to use all of its edges anyway. There's no reason not to. because I don't know, like it's a pretty basic greedy principle, I guess. So if one node is empty, we just use everything. Yeah, well, what if we like sort them by their differences, maybe? It's not clear, even if we so we've got this graph 2 1 1. Oh, maybe we picked this item last. Yeah, oh, maybe it's a top sort. Ah, I see. Well, hang on. So what if... Does that argument hold then that what if there's nothing you can start with? Nothing with like degree... Nothing with degree less than... or equal to its number. Does that mean it's impossible? 2 3 1 1. Well, if there's nothing with degree less than or equal to its number, then you can't actually, like when you remove an edge, you remove a number by 1, you decrease a number by 1, you also decrease the degree by 1. So that property will stay true. So then you have an issue. Yeah. Cool. That's a cool problem. I know how to do it. Yeah, so E and F were cool. I wasn't really a big fan of A through D, but that's fine. They weren't like, they weren't bad. Assuming this is right, we'll see. So enter a values equals fs dot read end. Yeah, so degree. Okay, so then Wait, so what do we do? So we pick these numbers, and this is the reverse order. Yeah, okay. Third degree, next. So the index is going to be I, the number will be values at I. Okay, so, well, array deck, nodes, array deck. NNs. Oh, now we need to do the edges. Nodes at A dot degree plus plus, nodes at B dot degree plus plus, nodes at A dot adjacent dot add, nodes at B dot adjacent dot add, nodes at A. If nn dot degree is less than or equal to nn dot number, then bfs dot add nn. Now array list integer ants, and then at the end, come on, at the end we want to print the answer. If ants dot size equal to n. -1, I assume? Or just dead, okay. Dead or alive, huh? So we want to print ants.get I first space. Okay, so print writer. That should be not too big of an issue. So now, well, not bfs dot is empty. Dot add next. What is this? Oh, next dot index. And then this needs to be +1. All right, so then for node n in, oh, we need to print the order of the edges, huh? Yeah. Yeah, I guess we need to print the order of the edges. Okay, well, we'll print the order of the nodes first and then fix it later. So for each node in next.adjacency, okay, so nn.degree minus if nn.degree is less than or equal to nn.number, then bfs.add nn. Okay, keep doing this as long as it's empty. If we pop all of them, then we're fine, otherwise we're not. So let's just check this here on a sample. Whoa, what's going on? For each node. Oh, if okay. Well, I have 3, 1, 2. So we've got 2. So 1 has 2. 2 has 2, 1 has 1. 3 has 1. So yeah, I think that's fine. So this is printing the nodes though, not the edges. So then we need an edge class. Then okay, so then this is the case. All right, so let's make our edges. So edges at I equals new edge from nodes at A to nodes at B, and index is I. Okay, so now we set these, now we sort our edges. Sort edges. 0 is the matrix plus set edges at I dot index plus 1 plus our space. All right, so how do we compare these? We want first we remove the 2. Yeah, so we care about the later, or the, I guess the earlier removed. And that's when we'll get removed. So int val, well, return. All right, this is sloppy code, but I don't think it's that big of an issue. So now these are things sorted by when they get removed. So start at n-1, 0, plus minus, going backwards. 3, 2, 1. Woot. One, 3, 2, 4. 5, 4, 1, 3, 2. Dead. Okay. Good. Nope. Almost. So that's dead. Let's just check this one more time, make sure printing is alright. Cool. Let's submit. So we're looking 7th place so far. Geothermal beat us. Good job to him. But I'm happy with 7th place. It's pretty good. Solve set very quickly. Yeah, not bad. Looks like no one's getting hacked, so I don't think system tests are obviously bad, and I'm pretty confident in all my solutions. So I'm not too worried. How about my friends? How are people looking? Struggles on D. It's a bit unfortunate. What is D? Yeah, I don't know. D is just like draw a picture on paper and you should see it pretty quick, I think. D also could have been very big bounds. I guess they had their fill with that with F, so it wasn't really necessary. Yeah, we should get a pretty decent picture of like where I'll place by the end of contest. So let's talk about solutions since we're here. So let's bring out the whiteboard and draw some pictures. All right, easiest to hardest as usual. Problem A. Okay, so problem A, you've got some regular polygon and you want to know if you can orient it in the correct angle. So maybe we've got like some hexagon. And it should be pretty clear that if we're going to have one of the lines on the x-axis and then another one parallel to the y-axis, then what you can imagine doing is like we can move one of the sides down until it's flush with the ground. So we can like just slide this straight down. We might have to rotate it if it starts randomly, but like if we draw it like this, then we can always make one of the sides parallel to the ground. And it doesn't matter which one we do because it's like symmetric since it's regular. So it'll look the same no matter which one we do. And now all the problem's asking is, do we have a side that looks like this? So in this case we wouldn't, but if we draw like a square, we would. Or if we draw an octagon, we also would. So how do we tell whether that would happen? Well, like we're gonna like start here, and then we're gonna have like some number of sides. And what we wanna know is, do we have like a side here, and then some number of sides after it? And then if we have this side here, like if we can rotate by 45 degrees or by 90 degrees, and then have the same picture, then if we rotate by 90 degrees again, we'll have this top side here flush with the, like these two will match, top and bottom, and then we'll have the left and right match as well. So that's like really the only way of doing it. If you tried to take like 3 steps and match this one, then if you took 3 steps again from here, you'd match this. Or I guess if you took 3 steps again, you'd go back 1, so you'd match this. So taking 1 step and taking 3 steps are the same. If like you mean like 1 step around the quarter circle. So yeah, so we have this, and now we have 4 groups that all look the same, and this will happen whenever n is divisible by 4. So here we've got these 2 edges in this group, and we have 2 edges in this group as well, etc. For the square, we would have just 1 edge in each group. for a 16 gon, you'd have 4 edges in each group, and then you'd have that same thing with the first edge rotated by 90 degrees, shifted over. So it's just like a check to make sure n divided by 4 is fine. That can't give you 0, right? Yeah, a 0 gon would be kind of silly. So that's problem A. Let's look at problem B. So in problem B, you have a binary string, and you want to make it lexicographically minimal. So maybe your string looks like this. So 0, 0, 1, 0, 1, 1, 0, 1, 1, 1. So what you can do is every time you have a 0 and a 1 together, you can delete one of the two characters. So what that should immediately tell you is if you can only look at things that have 1s followed by 0s, then any 0 prefix you're stuck with, and any 1 suffix you're also stuck with. Because like the things that come after here are either going to be a 0 or a 1. In either case, you can't delete them. And the things that come before the suffix will either be a 0 or a 1. But in either case, the only thing you can delete is a 1 followed by a 0. And that'll never happen for this prefix or this suffix. The other thing to keep in mind is you can only delete, like, so we can like conceptually just erase these because they're not relevant. I'm not going to erase them, but let's maybe just like move this part down. But you can imagine erasing them, and that won't change the answer because these will never be part of any pair that you can make to delete something. So now what you'll notice here is we're going to start with a 1 in this extra substring, and we're going to end with a 0. And we can delete all but one of these characters. And the reason why is we can always delete the second character, or we can always delete the second last character. That's not true. So, yeah, that's not necessarily true. But like the first 0, we can always delete unless we have like all 1s. And if we have all 1s, we can delete the last one. And you can always delete that until you have just 1, 1, and 1, 0 left. And now when you have a 1 and a 0 left, you just have this prefix here and this suffix here. And now you get to either put a 0 here or a 1 here. And after that, you can't make any more moves. You can't delete anything. That's it. You're done. So you want it to be lexicographically minimal, and you can do that by putting the 0 in instead of the 1. So yeah, that's problem B. So actually, like for implementation details, we have company.
Understood, sir.
For implementation details, what you have to do is you have to count the prefix of 0s, count the suffix of 1s, and then I guess you have to special case like if it's all 0s or all 1s, and then you find the first 0 here, so you're going to keep this, and then you're going to keep this, and then it's possible they overlap. So if they overlap like this, then you just keep the whole thing. All right. Problem C. Lee just became a master. What is this problem again? Oh yeah, you've got your friends. Your greedy friends. So that's fine. So you yeah, okay. So you have like you want to maximize the sum of the minimums plus the maximums that each friend gets. So I think this first sample was actually pretty good. 1, 13, 7, 17, and then you have 2 friends, which get like you've got one bucket of size 3 and one bucket of size 1. So now we're gonna handle like the minimums and the maximums separately. So for the minimums, what you want to do is you want to bunch them up as much as possible. So if you have like a bunch of small things that like increase like this, like let's say this is kind of your graph of values. So like this will be, like imagine you sort your array. Now this is like the position in the array, and then this is the value of the ith element. So if you want your minimums to be as big as possible, what you're going to want to do is you're going to want to split it up like this. You're going to want to split it up so that like your big chunks take out, you want to remove as many of these small elements as possible. Because you know that this element here is going to correspond to some bucket. It doesn't matter which bucket it corresponds to really, but you want to make sure that the rest of these values, you want to skip as many of them as possible. So you're going to put all of these small values in your biggest bucket. And then after you do that, you're going to take this next bucket, and this will be your next biggest bucket, and you want to put as many of these values in here as possible. And then you keep doing this. So your bucket sizes get smaller, which means the things that you actually look at become more dense as the values get bigger. So as you're looking at bigger values, you take more and more of them as your minimums. Now as your maximums, you don't want to compress your maximums at all because you want every big number to be counted toward your sum, since they're all positive. They are all positive, right? Oh, wait. They're not all positive. It doesn't matter though, because we could, like, we're picking a fixed number of numbers every time, and since we're picking a fixed number of numbers every time, we could add 1 billion to all the numbers, and we just add a fixed constant to our total. So we can imagine it as if they're all positive. So, yeah, so for these big numbers, you want to count each of them separately. And the reason you want to do that is because they're all big, they're all as good as you can get, so you don't want to compress any of them. Whereas the small numbers, you want to compress as much as possible. So what you can do is you can sort your buckets by size, and then you can also sort your numbers by size. So what our numbers will look like here will be like 1, 7, 13, 17. And we'll make this a maximum for this bucket. We'll make this a maximum for this bucket. And if we had a third bucket, we'd make this the maximum for it, but we don't. And now we have these leftover numbers, and we're going to put these in the biggest buckets possible. And that'll be our assignment. So this is kind of like very few numbers, so let's look at a slightly bigger example, just because we have plenty of time before the round ends. So maybe we've got like 1, 2, 2, 3, 3, 3, 7, 10, 15. And maybe our buckets look like we've got like one of size 4, one of size 3, and one of size 2. So I've got my values sorted in increasing order and my buckets sorted in decreasing order. And now here's how I do it. So I take the 15, 15 goes here. I take the 10, which goes here. I take the 7, which goes here. And you want to do that because you want all of these to be counted. You want your bigger numbers to be counted. So that's why I used all of those. These zeros are a little bit distracting, so let's draw it like this. 15, 10, and 7. So now all of these have been used. Okay, so now I want to count these small numbers as little as possible. So what I'll do is I'll put them in this biggest bucket. So I get 1, 2, 2. And now I've counted this 1, which I had to do anyway, and I've removed as many of these as possible. And now I'm going to put some 3s here. So I put 2 3s here and 1 3 here. So this will get me a bunch of these numbers. Okay, so now I have like these numbers, or I have these sets, and this is like how you could extract the sets if you needed to, but it's also just really easy to take the first and last number from each set, and that'll be your answer. Cool, so that is problem C. Kind of took a while to explain, but I think I did a good job explaining it. So that's fine. Problem D. Yeah, this one is interesting, I guess. So you've got a couple things. So here's your layer 1, which never really matters to me. Here's layer 2. Layer 3, we do this. Layer 4, we do this. Let me draw it slightly differently. So we do this. So let's put some labels here too. So this is 1, 2, 3. This is 4. And what you'll notice here is, I guess I'll do 5 too. Just so here's 5. So 5 is this node here. It's not going to be enough room. So you've got your first node with 3 kids. Then your first kid is going to be this entire 4. The left kid is going to be the 3. and then the right kid will be another 3. Okay, so what you'll notice is in each of these, you've got the main child here, and this main child is just going to be the one right before you. So this, for group 4, it's this 3. For group 5, this main child here is just going to be equal to the 4. And you can prove that inductively, but I don't feel like proving it. And also, like, the pictures I feel like are much better proof than any formal logic could do. Formal proofs are kind of a waste of time for explaining things, in my opinion. And then you have these 2 side kids as well, and these are always going to be equal to 2 before you. Like they're one step behind, basically. And you can see that like in the 3. So in the 3, you have this size 2 as your first thing, and these 2 are both one step behind. So they're both 1s, but then they'll turn into 2s next time. So what you can do is that counts for most of it. There's one thing we're missing here, but basically we can do an easy DP. So let's do the DP in another color, maybe in red. So DP at I is going to be equal to DP at I minus 1, or I minus 2. No, I minus 1. So that's going to be this middle part right here. So it's going to be the answer for that, plus DP of I minus 2. And this is going to be pretty much the answer. We also might need to add 1. So when do we need to add 1? Well, in step 3, we need to add 1. And the reason why is we can pick this group right here. And the reason we can do that is because we don't pick the root node for either 2 or for 1. So this is like a check mark, I guess. So this is open, this is free, and this is free as well. But then this one, since this is free and this is free and this is free, we can pick a claw right here. So now this is going to be used. So I guess I'll just make an X here. So now there's an X here, which means we can't make the 4. But for the 5, we're going to have an X here, and we're also going to have an X here and an X here. So we can't make this either. For the 6, though, you can imagine we would have 2 5s and a 4. So we would have both of these next to each other, and we would be able to pick it, so we have to add 1. So one way of seeing that, if you just draw it out, is you add 1 every 3 steps. The other way of looking at it is that you add 1 if the previous 2 turns you didn't add 1. So yeah, I guess that's the goal. So yeah, so like plus 1 if I mod 3 equals 0. Why? I guess there's a little bit more that I should show. Why do we want to pick this claw here instead of picking this claw here? Well, if we can pick this top claw here, we might be able to use this for something else in its parent. But we know we can't use this for anything else. So we can use some exchange argument anytime we pick this. We should instead pick this. And that will never make our answer worse, but it might make our answer better. And we can, if we push our claws as low as possible, then we can always pick as many as possible. So yeah, I think that's it. Last thing I'd like to talk about. You can do this for bounds that are much bigger. So the problem makes the maxed bound equal to 10 to the 6th, and that lets you just do this DP. But since this DP only cares about a couple things, the only thing it cares about is DP of I minus 1, and then it cares about DP of I minus 2, and then it cares about the constant 1, and it cares about I mod 3. So what this formula right here is it's a linear combination of each of it's a linear combination of these 4 things. And what we can do is we can write this in a matrix, and then we can take this matrix to a really big power. And that will let us calculate what these DP values will be for, like we can calculate the DP value of like some term in logarithmic time. So if we have like 50 test cases, and each test case has up to the 10 to the 8th level, then we can calculate that as well. So we don't have to do it in just linear time. We can do it a lot faster. But like it's a div 2 problem that might be a little bit overkill, a little bit unnecessarily difficult. Okay, problem E. So in problem E, you have a bunch of like different types of food and a bunch of friends, and each friend has like 2 favorite types of food. They'll either eat both if they're both available, otherwise they'll eat one if one's available. Otherwise, if neither are available, then you lose. So as with a lot of problems, if you have a bunch of a bunch of different types of things, and then also you have a bunch of like pairs of things, it might be helpful to look at it as a graph problem. And in this case, you have a bunch of different nodes, and each node is a type of food. And maybe it looks like this here. Maybe that's your graph or something. And you can have multi-edges too. So maybe you've got that and that. You just can't have any self-loops because no one has 2 favorite foods that are the same. But yeah, okay, so you've got this graph. And then what you can do is you can, like, each node has some number. So maybe the numbers are like 5, 3, 1, 2, 1, 2. So what you can do is you can delete some edge, and you can lower the number on both nodes by up to 1. So maybe this turns into a 1, this turns into a 4. Then maybe we do the same thing again. So now this turns into a 0, and this turns into a 3. And you can do that as long as at least one of the nodes is positive. You can't do it if they're both 0, and you can't do it if either are negative. So how do we like solve this problem? How do we come up with a way of doing it? Well, let's kind of look at it backwards for a little bit. So the last node that we take an edge from, whatever that last node is, we know, like, or hang on, give me like 5 seconds to think. Yeah, okay. The last node that we take an edge from, when we took that edge, we decreased it by 1. So from that, we know every time we took an edge from that node, we decreased it by 1. The only 2 things you can do are you can decrease it by 1 if it's positive, or if it's 0, you can get it for free. But in all other cases, it has to be like in the very last node that we take, when we take it, that means we decreased it by 1 for that edge. And it also means for every previous edge, it was also positive. So we decreased it by 1 for every previous edge too. So, okay, let's look at the graph when it's empty and kind of build backwards from that. So when the graph was empty, we initially just have, I guess let's just say we've got this top number, and we'll ignore what the numbers are for everything else for now. And this was the last edge we took. So after we took it, this had a value of 1. That means before we took it, this would have had a value of 2. And that means it's definitely safe to undo all of these edges at the end. Because when these edges were taken, that means this thing had 1 subtracted from it. So let's take from all of them now. So now we have these all as value 2. And maybe now before that, we had some edge here that had like these 2 edges. And we don't know whether we subtracted 1 when we took this white edge. It's possible this thing had a value of 0, and then when we took this white edge, the value stayed 0. But for these 2 edges, if this was the first edge we took before we took all 4 of these white ones, then we know that we did subtract 1 from this one as well. And it's possible it wasn't this one, it's possible it was this one instead. But for whichever one subtracted 1 for, let's say it was this one, then for this edge and this edge, we subtracted 1 from its degree for both of them. So what we can do, like basically I guess the formal way of looking at it is if whatever your number is, if your number is greater than or equal to your degree, that means it's safe for you to just take all of the positions that are left. Yeah. So let's say this is our graph. We'll just make it very simple. If this has 5 like meals of food left, you can take all 4 of these because you won't run out of food here. And that will like definitely be some way of doing it. I guess let's prove when it's impossible. So if you have a bunch of nodes, and for every single node, you know the number on that node is less than its degree, that means every time you take an edge, that property is still true. So every time you take an edge, for one of the nodes at least, you have to subtract 1 from both its degree and its number. Like for the last edge you take, for the yeah. So if nothing ever gets emptied, if no edge is ever emptied, then when you take an edge from something, you subtract from both its degree and its number. And if you keep doing that, you will have problems because you'll have a number of 0 and a degree that's positive. So that's, I guess, why it breaks. So yeah, that's kind of a little bit of a hand wavy proof. If you like understand the intuition, it should be more understandable, I think. But yeah, so all right, so here's the idea. So we're gonna do like a top sort. So when we have something whose when we have something whose number is greater than its degree, then we add it to our queue, and we're gonna process things like from the end to the beginning. And then once we have chosen some order of nodes, like some top sort of nodes basically, then we can go backwards and do all of the edges in reverse. So whichever node was removed first, that's when its edges were removed. So we can sort all of our edges by when the nodes were first removed. And then we did this all back in time, so then when we print the edges, we have to print them in reverse order. And then when we pick an edge, when we remove a node, obviously, we also decrease 1 from the degree of all of its neighbors, because they wouldn't have to pay for it, since they may have been 0 at the time if they wanted to be. Okay, so that's the implementation details. Last problem, problem F. Problem F was a cool problem. I enjoyed it. I guess it's because I solved it pretty quick, but it's still a cool problem. So yeah, there have been like problems like this before. This is a somewhat common idea, where the winner or loser of some round gets to choose who begins the next round. And the idea for this is, if you don't know whether the next round you want to be the winner or the loser beforehand, so you want to store for each round both whether you can win the round and whether you can lose the round. And then like if you can either win or lose, then you get to choose whether you move first or you move second in the next game, in the final game. So then in the final game, you'll just pick whichever player you want to be. So it's possible you can force yourself to be the first player. It's also possible you can force yourself to be the second player. And it's possible you can force yourself to be both or force yourself to be neither. Like you don't get to choose, your opponent gets to choose. So you want to keep track of which case you're going to be at for each game. So the first part of the problem, I guess, is solving the game itself. So you want to say, like, if you have some game, maybe 10 is your biggest number, and then you've got numbers like 9, 8, 7, 6, 5, 4, 3, 2, and 1. And there's going to be like some minimum starting cutoff. So, but we can like process these naively. So let's say whether we can force a win, and also whether we can force a lose. So if the maximum number is 10, if we go above 10, then we're going to lose no matter what. So we can't force a win because our two choices are go to 11 or go to 20, both of which will lose. And we can force a loss. If we want to lose, we can lose at 10. We can also lose at 9, 8, 7, and 6 because each of those we could choose to double. And if we choose to double, then we will lose. So at 9, 8, 7, and 6, we can force a loss if we want to. At 9, we can force a win as well, because if we go to 10, then our opponent will lose. So at 9, we can force a win. But at 8, if we add 1, so our two choices at 8 are 9 and 16. If we go to 9, then our opponent can make himself win. And if we go to 16, we lose right away. So in both cases, we can't make ourselves win if we're at 8. And at 7, if we go to 8, then we just determined we can't make ourselves win. So if we're at 7, we can force it to be our opponent's turn at 8, and our opponent won't be able to win. So that means we can force ourselves to win if we're trying to win at 7. We can also force ourselves to lose by just losing right away. And then at 6, we can reach 7, in which case our opponent can force a win. Or we can force a loss by going to 12. But we can't force, we can't win at all. So we lose at 6. And then, okay, at 5 you can reach 6, so you can force a win. But at 5, you can reach, if the goal of this game is to lose, you can't lose at 5 because you can reach 10 or you can reach 6. In both cases, your opponent can force a loss. So you can't force a loss. 4, you can reach 8. So this is just going to be a 1. 3, you can reach 6. 2, if you're trying to win, you can reach 4 or 3. In both cases, it'll be your opponent's turn and they'll be able to win. So you can't win for 2. And then for 1, you can reach 2. So if it's your opponent's turn and it's their turn 2, then they won't be able to win. So that means you can win by making it their turn at 2. So what you'll notice is, let's just look at this force win column right here. There are kind of two patterns you'll see. The first pattern is it alternates 0s and 1s. And this will happen if the top thing is a 0 and then you have a bunch of 1s above. So if anytime above you go to 10, then anytime if it's 11 and it's your turn, that means your opponent just made it your turn at 11, so your opponent just lost. So you have a bunch of 1s up here. If you have a bunch of 1s above, that means that the only way to win is to go 1 step up. And that means it'll alternate. It'll switch between 0s and 1s. The other case is you'll have a bunch of 1s. And this will be the case if whenever you multiply by 2, you hit one of the 0s. So in each of these cases, we'll get a series of 1s. And it turns out what you'll have when you draw this out is you'll have a bunch of alternating 0s and 1s, and then a bunch of 1s, and then a bunch of 0s and 1s, etc. And this is nice because this is a very predictable pattern, and there are log n different groups, so we can iterate through each of the groups. The other case, which is kind of interesting, is let's say instead of 10 it was 9. And you'll see the same thing in this force loss column. So let me evaluate a couple more. So for 4, you can win because you can hit this 5. For 3, you can, you're in trouble, you're going to lose because you can either hit the 4 or the 6, both of which are 1s. For the 2, you can win because you can hit the 3. And for the 1, you can hit the 2 or the 2, so you lose no matter what. Or you can't force yourself to lose because you can't force your opponent to win. So yeah, here you have the same thing. You have this chunk of size 5, and then you have this alternating chunk here. So what you'll see is when the size of your chunk is odd, it'll keep alternating forever. Because whenever you multiply by 2, you'll hit another thing of the same parity, another thing that's also a loss. In this example, when you multiply 4 by 2, you hit something that's, when you multiply one of these by 2, you'll hit something where your opponent can win, which means you'll lose here. So that's not true. We care about the 0s. So when you're at, so this is 1. So here's your odd number. When you take your odd number and you multiply it by 2, you'll get to a 1. When you take this odd number and you multiply it by, 5. Yeah, so anytime you multiply a number by 2, you'll hit a 1. Which means multiplying by 2 will never help you achieve the goal that you want. Because if you're trying to lose, that'll mean your opponent can force themselves to lose. If you're trying to win, that means your opponent can force themselves to win. So it's never helpful to multiply by 2 if this thing here is odd. If the thing is even, then when you get to the n over 2, you'll start being able to multiply by 2 in order to force a win. And then in that case, you'll have this just string of consecutive 1s. And then after this, you'll have 0s and 1s possibly alternating. So you can do this recursively. You just need to check whether it's odd or even. And then you also need to check whether you're a string of 0s and 1s or a string of just continuous 1s. So that's how you worry about a single game. So now, basically, what we've done is we've simplified this entire problem from, instead of being this really complicated multi-game nonsense, to just being, okay, if we have a single game where you start at this value and the maximum legal value is this value. So this is the one game we're looking at. We can say whether you can force a win or force a loss. That's what we've been able to do. Okay, so now we've like black boxed that. So now what we can do is we can like rewrite this thing to be, we're gonna play some game, and like the winner, or the person who goes first, so this is like the first person, this person can either force a win, possibly, or maybe they can force a loss. And we can determine both of these things in log time by doing what I just explained. So now what we know is if they force a loss, that means they're going to be player 1 in the next round. And if they force a win, that means they're going to be player 2 in the next round, because the losing player goes first. So basically what that means is in the next round, if we've got this for this current round, now we have this next round, whatever it is, and in the next round we've got some game. Maybe the next round can force a win, and maybe it can force a loss. So maybe let's say both of these are 0. So if both of these are, like, if the player who goes first can't force either a win or a loss, then what you want to do is you want to be the player who goes second, because that means the second player gets to choose whether they win or whether they lose. And if you want to be the second player, then you want to win this first game. If you win the first game, then you can either win or lose the second game. So what we can do is we can see, okay, do we want to be, can we choose which player we are? And if we can choose which player we are here, then we can choose which player we are in the future. And if we can't choose which player we are here, then our opponent can choose whichever player they want, and then they can choose whatever outcome they want for this match. So we can process these matches in reverse order. You can probably also process them in forward order as well. But you can say, yeah, I guess maybe forward order is easier. I implemented it in reverse order, but it might be cleaner in forward order. So like initially, you're forced to be player 1, and you cannot be player 2. Then after this first round, you know whether you can force a win or force a loss. And if you can force a win, that means you're allowed to be player 2. If you can force a loss, that means you're allowed to be player 1. So now we have this next game here. So now you can be player 1. There are like 2 different cases. The first case is if you can be player 1 here and you can force a win. So if the person who goes first can force a win, that means, can force a loss. If you force a loss, then you can be player 1. It's also possible if the person who goes first can't force a loss, and you can force yourself to go second, that means the second player gets to choose who loses. So if the second player gets to choose who loses and you go second, that means you're allowed to force yourself to be player 1 in the upcoming round. And okay, so there's also, you can reverse that. So if you want to be the person who wins, then if the person who's going can force a win, then you can choose yourself to go second in the next round. If the first person can't force a win, that means the second player chooses who wins. And the second player, if you can be the second player, if you're allowed to be the second player here, then you can be the second player in the upcoming round. So you can like do those 4 cases, I guess, just like work through it by hand and figure out what it would look like at the end. Okay, so I think that's pretty much the end of contest. It's also the end of the review. Oh, one for my friends, it looks like. Cool, yeah, so it looks like 8th place overall. It's not bad. I'm pretty happy with that. Solved set. Hope you guys did well as well, and hope you enjoyed the problems. I thought the last 2 were both very, very cool problems. I always enjoy game 3. It's always fun. Requires some thinking and then not too much coding, but they're fun to do. Yeah, so good luck on system tests and hope you enjoyed.